National Electrical Code Section 250.106 mandates bonding to the grounding electrode system, but relies on other sections for specific sizing guidance. National Electrical Code Section 250.66 is the governing section for sizing the bonding jumper connecting to the grounding electrode system. To properly size this bonding jumper, you must refer to National Electrical Code Section 250.66, which provides tables and guidelines based on the size of the ungrounded service conductors. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Firstly, determine the size of your service entrance conductors. This is critical because the size of the service entrance conductors directly dictates the minimum required size of the grounding electrode conductor. Secondly, consult National Electrical Code Section 250.66. This section contains a table that correlates the size of the service entrance conductors with the minimum size of the grounding electrode conductor. This table is essential for ensuring compliance with the NEC. Thirdly, locate the row in the table within National Electrical Code Section 250.66 that corresponds to the size of your service entrance conductors. The corresponding value in the adjacent column will indicate the minimum size of the grounding electrode conductor required for your system. If you have multiple grounding electrodes, the conductor that connects to those electrodes is sized using National Electrical Code Section 250.66. Keep in mind that this section provides minimum requirements. In certain situations, it might be advisable to use a larger grounding electrode conductor than the minimum specified in the code. This decision should be based on engineering judgment and consideration of specific site conditions. The grounding electrode system may consist of various elements. This includes metal underground water pipes, concrete encased electrodes, ground rings, and rod and pipe electrodes. Each of these elements contributes to the overall effectiveness of the grounding system. When dealing with metal underground water pipes, they should be supplemented by an additional electrode. This is because metal water pipes can be subject to corrosion or disconnection, which could compromise the integrity of the grounding system. Concrete encased electrodes, often referred to as UFERs, are typically installed during the construction of a building. They consist of a length of steel reinforcing bar or conductor encased in concrete that is in direct contact with the earth. Round rings are continuous conductors that encircle a building or structure and are buried directly in the earth. They provide a low impedance path to ground and are particularly effective in areas with poor soil conductivity. Rod and pipe electrodes are driven into the ground and provide a direct connection to the earth. They are commonly used as supplemental electrodes or in situations where other types of electrodes are not feasible. When installing ground rods, proper spacing is essential to ensure their effectiveness. The general recommendation is to space ground rods at least the length of the rod apart. This helps to minimize the overlap of their effective grounding zones and maximizes their ability to dissipate fault current. The bonding jumper plays a crucial role in connecting various components of the grounding system together. This includes bonding metal enclosures, equipment grounding conductors, and the grounding electrode system itself. The purpose of bonding is to create a lower impedance path for fault current to flow back to the source, which facilitates the operation of overcurrent protective devices such as circuit breakers and fuses. When sizing bonding jumpers, it's important to consider the potential fault current that the jumper may be required to carry. The size of the bonding jumper should be sufficient to handle the available fault current without overheating or failing. Factors such as the impedance of the fault current path and the clearing time of the overcurrent protective devices should be taken into account. In addition to the minimum size requirements specified in the NEC, there may be other considerations that influence the selection of bonding jumper size. For example, in industrial facilities with high levels of electrical noise, it may be necessary to use larger bonding jumpers to minimize the effects of electromagnetic interference. Similarly, in areas with corrosive environments, it may be necessary to use bonding jumpers made of corrosion-resistant materials to ensure long-term reliability. Proper installation of bonding jumpers is also crucial for ensuring their effectiveness. Bonding jumpers should be securely connected to the equipment and enclosures they are bonding, using appropriate hardware and techniques. The connection should be clean and free of corrosion to minimize impedance. The length of the bonding jumper should be kept as short as possible to minimize inductance, which can impede the flow of fault current. Regular inspection and maintenance of the grounding and bonding system is essential for ensuring its continued effectiveness. This includes visually inspecting bonding jumpers for signs of corrosion or damage, tightening connections as needed, and testing the impedance of the grounding system to verify its integrity. Any deficiencies identified during inspection should be promptly corrected to maintain the safety and reliability of the electrical system. National Electrical Code Section 250.66 outlines the requirements for grounding electrode conductors. These conductors connect the grounding electrode to the service equipment or separately derived system. The size of the grounding electrode conductor is based on the size of the service entrance conductors or the output of the separately derived system. If multiple grounding electrodes are used, they are connected together to form the grounding electrode system. The size of the bonding jumpers used to connect these electrodes is also determined by National Electrical Code Section 250.66. It's important to note that National Electrical Code Section 250.66 provides minimum requirements for grounding electrode conductor size. In some cases, it may be necessary to use a larger conductor to provide adequate grounding protection. Factors such as soil resistivity, the presence of sensitive electronic equipment, and the potential for high fault current should be considered when determining the appropriate size of the grounding electrode conductor. When dealing with existing electrical systems, it's important to verify the adequacy of the existing grounding electrode system. This may involve performing ground impedance testing to ensure that the grounding system is providing a low impedance path for fault current. If the existing grounding system is found to be inadequate, it may be necessary to upgrade the grounding electrode conductor or install additional grounding electrodes. In summary, National Electrical Code Section 250.66 is the primary reference for sizing bonding jumpers and grounding electrode conductors. Careful consideration of the factors outlined in this section, along with sound engineering judgment, is essential for ensuring the safety and reliability of electrical systems. Regularly review the latest edition of the National Electrical Code to stay up to date with any changes or revisions to these requirements. In addition to the specific requirements outlined in National Electrical Code Section 250.66, there are other related sections of the NEC that provide guidance on grounding and bonding. For example, National Electrical Code Section 250.4 provides general requirements for grounding and bonding, including the requirement that grounding systems be designed to limit the voltage to ground on electrical equipment and prevent dangerous voltage from appearing on metal parts. National Electrical Code Section 250.24 provides requirements for grounding separately derived systems such as generators and transformers. This section outlines the conditions under which a separately derived system must be grounded and the methods for accomplishing this grounding. National Electrical Code Section 250.30 provides requirements for grounding electrode systems, including the types of grounding electrodes that are permitted and the methods for installing them. This section also includes requirements for the bonding of metal water pipes and other metal structures that may be used as grounding electrodes. National Electrical Code Section 250.50 provides requirements for the common grounding electrode system, which is the system used to connect all of the grounding electrodes together to form a single, unified grounding system. This section outlines the requirements for the size and type of conductors used to connect the grounding electrodes, as well as the methods for making these connections. In addition to the requirements of the NEC, there may be other applicable standards and regulations that govern grounding and bonding. For example, Underwriters Laboratories UL publishes standards for grounding and bonding equipment, such as ground rods, grounding connectors, and bonding jumpers. These standards provide requirements for the performance and safety of these products. The Institute of Electrical and Electronics Engineers IEE publishes standards and guides on grounding and bonding practices, which provide detailed guidance on the design, installation, and maintenance of grounding systems. These standards and guides are widely recognized and used by electrical engineers and contractors. When designing and installing grounding and bonding systems, it's important to consider the specific characteristics of the site and the electrical equipment being used. Factors such as soil resistivity, the presence of corrosive substances, and the sensitivity of electronic equipment can all impact the performance of the grounding system. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install ground-enhancing materials to improve the conductivity of the soil. In areas with corrosive substances, it may be necessary to use grounding electrodes and conductors made of corrosion-resistant materials, such as copper-clad steel or stainless steel. When dealing with sensitive electronic equipment, it may be necessary to use special grounding and bonding techniques to minimize the effects of electrical noise and interference. This may involve using isolated ground systems, shielded cables, and other noise reduction measures. Proper documentation of the grounding and bonding system is also essential for ensuring its long-term reliability. This documentation should include detailed drawings of the grounding system, including the location of all grounding electrodes, conductors, and bonding jumpers. The documentation should also include information on the size and type of conductors used, as well as the methods for making connections. In addition, the documentation should include records of any inspections, tests, or maintenance performed on the grounding system. This documentation should be kept in a safe and accessible location and should be updated as needed to reflect any changes or modifications to the grounding system. By following these guidelines and best practices, you can ensure that your grounding and bonding system is properly designed, installed, and maintained, providing a safe and reliable electrical system for years to come. Also remember that local amendments can exist. Always check with your local authority having jurisdiction to verify the local requirements.